We'll start with chapter 6 today. I expect it's going to take about 3 days to go all the way through chapter 6. So probably won't have a test until maybe a week from Wednesday. And pretty much what we've done, we've talked about an awful lot of what we're going to talk about for the rest of the semester. So the rest of the semester, I won't say is a review, because we do have to dial in some things quite a bit tighter than what we've talked about previously. But we've touched on just about everything at this point that we're going to cover for the rest of the semester. Probably the most complicated things, well, there's going to be something that's a little bit more complicated in every section that we talk about, but some of the more complicated things would be, like for this particular chapter, would be voltage rectification, which we'll talk about on Wednesday. And I'll tell you why we've got to talk about it here in a bit. And then we've got to talk about later in the semester emission from the X-ray tube and what controls the emission from the X-ray tube and how those things affect the X-ray beam specifically. So there's still some complicated things that we've got to talk about, but most of what we have to cover we've already talked about at least once. So not a lot of surprises, but it's just more intense and more in depth. All right. So I'm going to bring the screens up. I'm going to show you a couple of things here in a little while. All right, so chapter 6 is all about the X-ray imaging system. We're going to talk about fluoroscopic systems and radiographic systems and combination systems, which are I won't say the most common, but they are what we refer to as general use rooms, where you can do pretty much anything that you want to do. They're most flexible, and you can do upper GIs, you can do barium enemas, you can do lumbar punctures, and plus you can do any kind of trauma. So we're going to talk about the components of each one of those today. So we're going to talk about everything that we have to have. We're going to talk about the operating console. Auto transformer we've kind of beat to death, but I am going to dial it in a little bit tighter and talk about where we measure our voltage in anticipation of it becoming kilovoltage. We'll talk about the control of milliamperage, and we'll draw out the circuit and all that, and the filament transformer. And I meant to bring one. And then we'll talk about phototimers, or exposure timers, and then we'll pull up there. So that's our plan for today. Is we'll go through page 99, kind of start towards page 100. So we'll see how it goes. If we wind up running out of time, then we'll pull up short. All right. So again, we've got two different types of X-ray rooms. We've got general purpose room. General purpose room we generally refer to as RF room. So RF room is radiography and fluoroscopy. So you can do any exam type in those rooms within reason. We can't really do, we used to, but we don't anymore, do things like cardiac catheterization or anything like that. That has evolved to the point where we need specialized equipment. It's usually going to be a C-arm type setup. So RF room is going to be a diagnostic room. It's not going to be a special procedures or a cardiac catheterization room. So the things that we have to have are, in order to create X-rays, is the equipment to give us high enough voltage that we can create X-rays. So what we have delivered to us ranges, and the most common ranges are the same things that you have at your house, 110 to 220 volts. Your dryer has a specific plug that plugs into the wall because it requires higher voltage than what your microwave does, right? So you've got two different deliveries of voltage levels, and it's the same thing in the hospital. Under certain circumstances, they may have delivered higher voltage, but it's never going to be higher or high enough to create x-rays. So we have to take the x-rays, or the energy, the electricity that we receive, we have to manipulate it to create exactly how much voltage and amperage we need. So this is going to be jumping ahead just a little bit, but here we go. What's the first thing the electricity gets to when it comes into the imaging system? We're not going all the way back to the power plant, but the first thing that the energy gets to is the auto transformer. So what are all the words that we use for auto transformer? Rheostat, right? It's a variable resistor. It's a variable turns ratio transformer, right? So what I mean by that is that we have specific contacts on which side would we call this? Supply the primary side with alternating current. Remember, we always have to have alternating current up at this point. So we have fixed contacts on the primary side, and what we do is we adjust the contacts on the secondary side so that we can adjust voltage. If we spread them out, our voltage goes up. If we squeeze them together, the voltage goes down, right? So we can specifically set our voltage. So we feed it voltage over here, and we adjust, manipulate our voltage on the secondary side, right? So then this becomes our kVp selector, okay? So add that in, it's our kVp selector, and we select kVp by adjusting the contacts on the secondary side of the auto transformer, right? So, but that's really not the first thing it gets to. Okay, I just hadn't had a need to tell you about this other thing yet, but now we've got to talk about it. So again, this is jumping forward just a little bit, but if you flip over to page 96, the top diagram, figure 6.6, what you've got there is the first thing it actually touches is what we refer to as a line monitor. Okay. So line monitor is placed before the auto transformer, and it's just a meter that tells us what our actual voltage is going into the auto transformer. So you're sitting at home, we're getting into summertime, or I'm sorry, we're getting into wintertime, your heat's gonna kick on, you're watching TV, you got all the lights on in the house, and the heat kicks on, what happens? What's that?
The lights flicker.
The light flickers or dims just a little bit. And that's because you've got all this stuff, you know, hooked up in your house, and when the heat kicks on, or in the summertime when the air conditioner kicks on, it's sapping enough of that electricity that you get that little dip and it comes back up. Well, the same thing happens in the hospital. So power companies supply us with that electricity, 110, 220 volts, and it, if they don't have a good way of monitoring that and adjusting for it, then the same thing would happen in a hospital. So, imagine all the stuff that's plugged in at the hospital. You have CT, MRI, you've got monitors, you've got beds that raise and lower, you've got massive air conditioners and heaters, right? So the voltage that's coming into the hospital may fluctuate by, 5 to 10 volts. And then you add in all that stuff, and it can really fluctuate. So has Amy gone through technique and talked about how much of a change in voltage or amperage you have to have in order to see a visible difference in the image? Does that sound familiar at all? Yeah? Okay. Okay. So the general rule is the baseline, just to see any kind of difference at all, or affect a change at all. You're not really going to see any difference, but to affect a change at all, the minimum change you would have to make in amperage is 30%. Okay, so you'd never make a change if you were repeating an exam. You'd never make a change of 30%. But that's a baseline of how much you would have to change in order to affect any real change at the image receptor. If you ever have to repeat an exam, it's because you either over or underexpose the patient by 100%. So you either need to double your mass if you underexpose the patient, or cut it in half if you overexpose the patient. Okay, and even then, between those two, underexposure is really going to be your culprit. You didn't give the patient enough dose, so the image receptor didn't get enough dose. Okay, so 30%. What is 30% roughly as it relates to a whole? In a fraction, 30% is roughly a third. Right. So it's roughly 1/3. How much of a change in kVp do you need to double your exposure? 15%, right. So what's 1/3 of 15%? 5, right. So 5. So 5 kVp is enough to affect any kind of change at the image receptor. So according to Bushong, the voltage that we have coming to us can fluctuate by that much, right? Now you add in all those other things, especially with the air conditioner kicking on, and you can have, if the air conditioner kicks on at the moment that you're making an exposure, you can have a significant drop in voltage, amperage at your machine that could affect the outcome at the image. You don't want that, because then you got to go back in, you got to make another exposure on the patient, and it's just at a patient dose. So what we have to have is set electricity that's coming into the system, and that's what that thing tells us. Okay, so now that goes into, and what is a part of what we refer to as the line compensation circuit. Okay, so really the line compensation circuit is the first thing that the electricity gets to. And the purpose for line compensation is to set our electricity so that we're gonna know what we have going into our auto transformer. Okay, you can kind of think of this as a surge protector, but it does more than a surge protector. A surge protector is just that. It's a surge protector. So if you have a surge in electricity, a surge protector protects your electronics from getting zapped, essentially. You got a lightning storm. If you have a good enough surge protector, it might protect it from that. Okay. A constant battery backup supply is more like what this is, but it doesn't work off batteries as far as I know. So what it does is it protects against spikes and valleys. Okay, so it's a surge protector, but it's also a constant supply. So it knows, how to adjust to give us the right amount of voltage before we get into auto transformer. Okay, if you look at your control panel, where do you see this? You don't, right. So the only time you're ever going to see this, and it's the first thing I'm going to show you, the only time you're ever going to see this is if you happen to work somewhere with a single phase machine. I'm not going to drop the screens, but I am going to turn on. I don't think I'm going to drop the screens unless I absolutely have to. All right, so this is, this is not something that you're going to be, a diagram that you're going to be tested over, but this has the line compensation circuit in it. So you can just do a Google search on this. This is the RadTAC. I just happened to find this morning. This thing right here says line voltage compensation. All right. So what you have up there is your voltmeter to tell you exactly how many, how much kVp you're going to be using. That's your milliamperage, your ammeter. And so what you've got in this is you've got MA selector, you've got a timer selector, and then up here, you can't really read this because it's kind of fuzzy, but you've got major and minor kVp control. So you don't see any of that really in this configuration on your machines, which is kind of a shame, because back when we used to have an occasional single phase machine, it was kind of fun to, twist the dials. Made you feel like a mad scientist. But now you're just pushing buttons and you don't get that nice clacking sound as you increase or decrease the stuff. But this thing right here says line check switch, and I can't really reach it. So can you see that dark line right there? Okay, so what you do, or what you would do, is you would push this button, and it's a toggle switch that flips back to this spring loaded. So it flips back to this orientation. You push that, and what it's going to do is going to move the needle on the voltmeter. It's going to move it just to where it's showing you how much voltage should be going into your auto transformer. If it's below that, then you make adjustments. Okay, if it's above that, you make adjustments. It should point right to that, and there's a V right there, so it should be pointing directly to that V. So you don't see this in a modern machine because it's taken care of in the system, okay? So when you read that through Bushong's, that's what it's referring to, is the line voltage compensation circuit. You don't see it in a modern system. It takes care of itself. It's computerized, so it automatically adjusts it before it goes into the auto transformer. Okay? Turn those off. Oop. Whoa, got dark in here. All right, so the first thing it gets to is the to the line compensation circuit. And that fixes the voltage before it goes into the auto transformer. Okay, so now we've got predictable voltage that when the air conditioner kicks on or the heater kicks on, we're not going to get that dip. That 5% fluctuation that we get from the power company, we're not going to see that. It's going to be a set amount of voltage that we're going to then feed into the auto transformer. It's important because our voltage, the voltage that we have, eventually is going to affect the kilovoltage that we have, right? We don't have kilovoltage yet, but if we know exactly what the voltage is that's coming into the auto transformer, then we know what voltage is going to go out of the auto transformer, providing our contacts are moving properly. Does that make sense? Mm-hmm. So we still have voltage at this point. So more on that here in a bit. All right, so that's the first thing it gets to. Our general purpose rooms, they have you know, a range of kVp and MA stations. And you'll get to clinicals maybe Monday, Tuesday, and you can play with your machine. You're going to have to turn the photo timers off, and you can play with the machine and see what yours are. Okay, so Bushong says 25 is lowest kVp. Maybe a Mammo. I don't know that I've ever worked with a machine that shot with as low as 25 kVp. 40 is usually the basement that I would see. And it says, you know, you can shoot with up to 150, and I have worked with some of those, but you never use that. You know, the highest kVp typically that you're going to use is 110, 120 kVp, but you could go above that. So that's the range, 25 to 150. Your MA stations are going to vary wildly depending on your machine and the manufacturer you're going to use. Some might not go below 200, some might go all the way down to 25 MA. And some may go up to 600, some may go to 1200. So, you know, it's going to vary wildly. So it could be 100 all the way up to 1200, and that's what you're going to be testing on. Yeah? Would you say that the ranges are the same for Mammo and X-ray? No. The Mammo machines, the maximum kVp is probably 50 in Mammo. The Mammo machine is totally different than X-ray. I mean, the construction appears to be the same, but the target material is different. There's no need for the high-level characteristic X-rays that we create. So the target material is going to be molybdenum instead of tungsten. The tube is going to be inside of the housing at a funky angle. Totally different. So Mammo's probably going to be 25 to 50 tops. Yep. All right, so general purpose, again, RF room is most flexible. Radiography just has an overhead tube frame, but for fluoroscopy, you know, if you're in an RF room, it's got a second tube, and that tube is inside the table. You know, the thing you pull across the patient is not the X-ray tube, that's the image intensifier. Okay, so you're actually shooting from under the patient. So the patient's laying flat on their back, then it looks like, you know, logically you're going to be looking at the patient, and you're used to having a patient lay on their back, and when they're laying on their back and you shoot a KUB, they're in what projection? It's AP projection, right? But if they're laying flat on their back and you're using fluoro, it's actually PA. So everything is reversed, okay? So once we get into next semester and we're doing esophagograms and things like that, you know, if the doctor rolls the patient into a position that doesn't really make sense to you, it's because everything is reversed, okay? So when we do an esophagram, we put the patient into a RAO position, so it's right anterior oblique. But what may look to you like a LPO is actually a RAO whenever they're fluoroing. Okay, so just understand that. So some differences, there's some differences and there's some similarities between RF rooms and radiography rooms. Okay, so unless you have a room that is specific for dedicated chest or something like that, then every room is going to have, the word that they use is couch. Have you been on a table? Anybody? Climb up on the table? Well, you have in lab, right? So what do you think of when you think of couch?
Comfortable.
Comfortable. I'm going to take a nap. You think you're going to take a nap on an x-ray table? No, they call it a couch. I think it's, okay, whatever. So the couch, the x-ray table, has to have certain aspects to it. So directly under the tabletop, I'm going to use table, directly under the tabletop is where you put your image receptor, right? So unless you're in our lab, you're not going to be taking image receptor out and putting it in, but that's where it goes, right? So that's what we refer to as Bucky. Potter-Bucky diaphragm is the official name for it. And it's got a lot of stuff, all right? And we're going to talk about that stuff later in the semester. But one is, and it's evolved over time, originally it just held the image receptor, but then a grid came into play. Purpose for a grid is to absorb scatter radiation, and then automatic exposure became a thing, so that's included as well. So what you've got then is that Bucky where you put your image receptor, and that's really the only thing that you see, but it has more to it, and some of those things you're going to manipulate from the control panel. All right, so a few things about the Bucky. One is it increases the OID. Okay, so if you put the patient's anatomy directly on the image receptor, you have as low a OID as you can possibly get, right? But you put the image receptor inside the Bucky under the table, then you're going to have at least a 3-inch increase in OID. Okay, so it increases OID, and the design of the table can minimize that, or it cannot minimize that. And we'll talk about those two designs in a minute. But regardless, the x-rays have to get to that image receptor. So what are our types of material? X-rays either don't go through something, and we call that radiopaque, or they do go through something, and that is what we refer to as radiolucent. Right, so what's missing in that? Yeah, we don't have radioparency, right? So anything that the x-ray beam might pass through can absorb x-rays. That means everything is radiolucent. So certain things are more radiolucent than other things, right? But if it passes through something, it may pick up some signal and deposit it, on the image receptor. So your the cushions, those little thin cushions that are on the table, also radiolucent. Also, though, if you're in a contrast in a room where you deliver contrast, if it gets any contrast on it at all, then that reflects an artifact on the image receptor. So the same thing could potentially happen if our tabletop, instead of being of uniform thickness, those lines are supposed to be perfectly parallel to each other. If they're not of uniform thickness, let's say they're fat at one side and not so fat at the other side, then this end is going to absorb more x-rays than this end, even if it's radiolucent. Does that make sense? Okay, so it has to be radiolucent, and the more radiolucency it has, the better off it is, because if it's less radiolucent, we're going to have to expose the patient to more radiation. So it has to be highly radiolucent, and it has to be uniform thickness, right? So most of the time what we're going to use then is going to be carbon fiber, which is extremely radiolucent. So the first time you have a patient who has an external fixator, be it on their leg or the halo, on their head, on their arm or whatever, you're going to look at the rods on that. And if they're black rods, then chances are what it is carbon fiber. And you can even take something metal and tap it, and it sounds like it's metal on metal. It's carbon fiber. And very, very radiolucent. You're going to think, okay, this thing is hard. It's going to absorb a lot of x-rays. So you take the x-ray and you can't see them. Or if you do see them, you only barely see them. Okay? Carbon fiber. It's hard and very, very radiolucent, but it still has to be uniform thickness. Regardless, the tabletops are big. So some may be plastic, but most of them are going to be carbon fiber. But they're relatively large, right? So they have to have some sort of support system. So, some of y'all have lab today. Take a look at the tabletop in lab. And what you're going to see is a flat tabletop. Okay? The other type of tabletop, Bushong refers to it as curved. I'm going to show you a picture here in a minute. And it could be curved, but those are usually a special application type tabletop. The radiography rooms or RF room tabletops that we'll refer to as curved aren't really curved. It's just that the bracing that would be underneath here and here on a flat tabletop is not underneath. Instead, it's over the top like that. Okay? So our lab equipment is like that. So a curved tabletop would look something like that. Okay, so you can see where the braces are, and it doesn't give you that three-dimensional perspective, but that brace sticks up probably, I don't know, maybe a 1/4 inch to a 1/2 of an inch. Not a whole lot, right? But is there potential positioning issues with the bracing being on the top? Kill that. Let me turn this off. And the answer is potentially, yeah. If you're doing let's say a decubitus chest x-ray on a patient, decubitus abdomen or decubitus chest x-ray, let's say chest x-ray and we've got a pleural effusion. A lot of flowing water in this guy's lungs. So you put your x-ray tube, on the far side, and the beam comes from a point spot and it spreads out. What do we call that?
Beam divergence?
Divergence, exactly. So you center directly in the center of the patient. You center directly in the center of the patient-ish. And what's happening with the lower portion of this x-ray beam? The divergence, right? So what's going to happen with your pleural effusion if your image receptor is sitting right here?
It's going to have to go through that.
It's a big hunk of metal, and it's going to have to go through it. So it's going to cast a mighty artifact, right? If you drop this down so that you can get the entire lung below it, drop it down below it, you still got a problem, right? That's that you're going to have this massive artifact that's going to cover your pleural effusion. You just can't see it. You might not be able to see it. So that's going to be a problem. So you're going to have to go in front of that, and you're probably going to have to build the patient up, or if you do go behind it, you're still going to have to build the patient up, right? So that's a drawback to the curved tabletop, is that, the support systems on top of the tabletop could give you an artifact on the image on things like cross-table laterals and decubitus and things like that. The benefit to those are, though, that if the bucky, has to clear these, well, let's say the image receptor is here, so the bottom of the bucky tray is here. how much of an increase in OID do we have from here to the image receptor? Compared to if the image receptor slides right there, and bucket tray is here. Which one gives us more OID? Yeah, this one. Okay, so both have benefits, both have drawbacks, they both have to have the same characteristic in that our tabletop has to be two things. Radiolucent, and what are you wearing? Your clinical, what's the word? Uniform thickness, uniform thickness, right? So has to be radiolucent uniform thickness. The benefit to this is that it decreases OID, right? The benefit to this is you don't have a problem with, that your cross table laterals and things like that. The support system getting in the way. You have less of a problem with it anyway. All right, so you got those things. So have you noticed that the way you move your tabletop around differs in different rooms? What do you notice about RF rooms? If it's a fluoro room, what do you notice? You're doing it. You got to push the button, right? You don't move it with your hands, right? It's motor driven. It's motor driven. And the other ones, what do?
Step on one.
Exactly. So what we have is motor driven and free floating tabletops. Benefits to both of those as well. The free floating, those are typically just going to be in your diagnostic rooms, not your RF rooms. You step on it and you can move the patient pretty quickly, and you can get them anywhere that you want to go with them. So you tend to see those in just your diagnostic rooms and your trauma rooms, things like that. The downside to those is that let's throw back to the last chapter, what controls those locks? What do we call that? I think somebody said it.
Magnets?
Okay, magnets, specifically we call that type of magnet almost solenoid, right? So you step on it, it goes clap. I can't hear if you don't speak up. I get that all the time. I'm supposed to hear that. All right, so it's solenoid. So you step on it, you hear the clack, and you can move it anywhere you want to. You get off of it, you hear the clack, and it locks into place. If that solenoid, or the thing that holds that thing still, starts to wear out, kind of like brakes on your car, and you lean up against that tabletop, bingo, that tabletop will run from you. Okay, now apply that to some of the fluoro exams that you've done. Anybody done a cervical myelogram? Okay, what do you do with a cervical myelogram? Don't ask you. Tilt the table, bingo. So if you've got a tabletop that has a tendency to move if you have some sort of pressure on it, and you put a patient on it, and you tilt that table, where's that patient going? Yeah, exactly. Straight into the floor. Straight into the floor. So we have to have something a little more stable, sturdy than that. So those are your motor driven. Again, fluoroscopy rooms, if it's fluoro, it's going to be motor driven. It's going to be slower, but it's much more stable. And most of the time, if you're doing a cervical myelogram, if you don't know, it looks pretty awful. But you're going to put the patient in boots, and you're going to strap those boots to the footboard on the table. All right, so it seems like a torture dungeon thing that you're doing to them, but it keeps them from falling on the floor. Still, if we had a floating tabletop, though, it very well could slide. The patient might not go to the floor, but you might give them a heart attack. So, motor-driven, fluoro rooms, floating tabletop, controlled with solenoids in diagnostic rooms. All right, so just real quickly, no, I already did that. Bucky has your image receptor holder, the tray, grid, and the AECs. One other characteristic of the floral room is that the tables do tilt, right? So they'll tilt in both directions in most cases. And they'll go all the way up to 90 degrees in one direction so that you can stand the patient on the footboard so that you can do things like upper GIs, barium swallows, start the patient upright. Right? You generally don't do that with a myelogram or anything like that, but with upper GIs, esophagograms, you usually start with the patient standing up. So a couple of things about that. One is your fluoro table is going to be identified by its degree of tilt. 90 degrees means the patient's standing right up, straight up. Horizontal would be, 0 degrees. So standing straight up, it'd be 90 degrees. If it went 90 degrees in both directions, it'd be a 90-90. You don't see that very often. Probably the steepest Trendelenburg head-down orientation I've ever seen was maybe 60, so it'd be like a 90-60 would be the degree of tilt. But that's how we identify that. But as far as footboard goes, the footboard can come off, right? So that if you're doing a modified barium swallow for, see post-stroke if the patient's swallowing well, that footboard has to come off so they can put that special chair in there, right? So you scoot the chair in there, you take the footboard off, you scoot the chair in there. So your next patient comes in, they're upper GI and they can walk, right? So you put the footboard back on. That footboard locks into place in specific places. So what you need to do is you need, be familiar with how the footboard goes on. And some of them, what they'll do, they've got one side that is fixed into place. You just kind of latch it on, and the other side kind of pivots out, right? So you put that thing on there, you clamp it down, but it's only going to go into a specific slot in that tabletop. So, this thing has a big chunk taken out of it where that's going to, fix itself, right? What I recommend that you do is if you're doing an upper GI, and you have to, even if somebody else put the footboard on, try to jerk that thing off of the, off the bottom of the table. Because what happens is that if they put it too high, it's gonna slide before it catches, okay? And if they put it too low, it's going all the way to the floor, okay? So, you get an upper GI, and before you raise the table up, you grab that thing and you rock it and see if you can pull it off. Because once the patient gets on it, if they step on it and then it slips, these are older patients most of the time, they can very well hurt themselves, right? It's like stepping off the curb. That's where we get a lot of our hip fractures, older patients stepping off the curb. So, and even if it's already on there, and even if it's already stood up, you get on it, get on it, stomp on it, and make sure it's not going to slide. So anyway, that's just your, public service now for today. Don't hurt your patient with the footboard. All right, so all your X-ray rooms are shielded against radiation. Doors, the windows are going to be leaded glass. The walls you can't tell, but they are. When we had our lab replaced, one of the things that they can do, they didn't get into the walls, so that there wasn't any real need to, but they can go around to the rooms around them and check for leakage radiation. If they had disrupted any of the walls, they would have had to do that. The doors in the lab, you ever felt how heavy they are? Look at the hinges on them. Hinges go from the top to the bottom. It's a solid core wooden door, but if you open the door just a little bit and look at the edge of the door, you'll see that there's a bump. It's laminated, but you can see that there's a little bump, and right under that bump is probably an 1/8 inch of lead. Goes all the way through the door. Okay, so the entire room might have an 1/8 inch of lead. It's shielded. There may not be any shielding in the ceiling and floor, because if you have like a foot of concrete, you don't really have to worry about it. And our external wall, I don't know if it has any shielding in it or not. If the X-ray room is above a certain level, height, then you don't have to have any shielding on the external wall, okay? I think it probably is, just because, you know, our local services that do that kind of construction they overdo everything. So if you're standing out in the vestibule area and somebody makes an exposure, you're getting exactly 0 x-rays. They just overdo everything, and I'm glad they do. Even the glass at the control panel is leaded glass. And I haven't done this with a digital image receptor, but back when we used screens and films, I wanted to see how efficient that leaded glass was. So I pointed I don't recommend y'all do this. I say that a lot, but I don't recommend y'all do this. But I pointed the x-ray tube directly at that glass, took a film, stuck it up against the glass where it was pointed and made an exposure, and I got nothing. Which makes no sense to me because I can see through that glass, but it is radiopaque enough that it absorbed every x-ray, you know, perceivable x-ray that hit it. So you're not getting much behind the control panel if you're getting anything. So all walls have to be shielded. All right. So principal parts of the imaging system, we're going to break it down to just 3. That would be your x-ray tube, which is obviously an x-ray room. The control panel, our operating console is what they'll refer to it as. And that's where you do all your manipulation of the beam to control the quantity and quality of x-rays. And we'll talk about everything else that we do, but quantity and quality, of course, is your kVp and your mass. And then you've got, he refers to it as high voltage generator. And in as much as we're taking a low voltage and making high voltage, it generates that. But a generator is generally something that generates electricity. All right, so windmills. You're taking mechanical energy and you're making electric energy. That's a generator, okay? So don't confuse the two. You know, in the reverse of that, you know, if you take electric energy and you make mechanical energy out of it, that's a motor. That's just pretty much a backwards wired generator. But what we're taking is low voltage and making high voltage out of it. In that context, it is a generator. It's generating very high voltage kVp. So we're going to talk next week about the different types of generators, right? So we've got single phase, 3-phase, and high frequency generators. We'll talk about those and the specifics of those on Wednesday. I keep trying to get y'all up here on Tuesday. All right. So the control panel, that's where we control everything. You know, you've got your potential. What is your potential? kVp, right? So it's kVp. kVp controls, in the x-ray beam, it controls quality, penetration. Because it controls penetration, it controls quality, right? In the x-ray tube, it controls how fast the electrons travel across the tube, right? Higher the kVp, the faster they go, the more kinetic energy they have, and the more kinetic energy they have, the more kinetic energy they have to lose, and therefore we create higher kVp x-ray photons. We also control focal spot. So as Amy talked about focal spot and its relationship to sharpness or recorded detail. Yeah, okay. We control focal spot there. The smaller the focal spot, the more sharpness. But what you're really controlling there is the size of the filament that you're going to use. So what do we put on and around the filament? We have a number of different words for it, or terms, or phrases, I guess. Create a space charge, which is thermonic emissions, right? So when we're selecting our focal spot, what we're doing is we're selecting which filament size that we're going to utilize. So applying the terminology thermonic emissions and knowing the main thing that we create in the x-ray tube is the main thing that kills the x-ray tube. If we put a lot of heat on a small filament, how long is that x-ray tube gonna last as opposed to putting it on a big filament? Not very long, right? So we have exam types that we want to use that small filament for, but most exam types we're going to use as big a filament as possible, okay? So you can select that. You can select the configuration of your photocells when you're phototiming, everything that you're going to want to do aside from positioning of the patient and the x-ray beam. That's where you control, as a control panel. So we've got kVp, MA, time. So kVp is going to be our quality, our penetration is potential, electric potential difference, speed of the electrons. MA is going to be our filament current, and understanding that we don't have kVp until we press the exposure button, right? We also don't really have mass until we press the exposure button. We have MA. Right? Whenever we push the prep button, we have MA, we create thermionic emissions, but mass is a measure of tube current. MA is a measure of filament current. Okay, big difference between the two. We're not making mass until we actually have tube current. Okay, so MA and time together gives us our our quantity. It's just the number of x-rays measured in milligray, and it's what we refer to as intensity. So at the control panel, we've got kVp, MA, time, focal spot size, which bucky we're going to shoot in, if we're going to shoot into a bucky at all, maybe shooting tabletop, which photocells, you know, how much exposure, just everything, right? So that's our control panel. X-ray tube comes in a different, different section. We already talked really about the high voltage transformer. High voltage transformer is not a variable turns ratio. It always has more turns on the
Secondary.
Yeah, I'm sorry, I'm pointing it the wrong way. Secondary side than it has on the primary side. So our voltage always goes up by a predictable amount. Always goes up by predictable amount, right? So if our turns ratio is 1 turn on the primary side to 100 turns on the secondary side, then our voltage is going to go up by 100 times. If it's 1 to 1,000, 1,000 times. If it's 10,000, 10,000 times. That's because it behaves according to the transformer law, right? Now, Bushong is going to talk about auto transformer, and you know he sneaks in the auto transformer law. Is it a different law? No, it's the same law. You know, I don't know why you put auto transformer law. It's just transformer law, right? They both work off the same law, and that is that the voltage change or the amperage change, you know, is predictable according to the turns ratio, the number of turns on the primary versus secondary side. Okay, more turns on the secondary side than the primary side, and voltage always goes up. More turns on the secondary side than the primary side, and our amperage always goes down according to that turns ratio. It's a law, so it happens every time, right? So the thing is, we got a couple of things. So everything that you want to touch and manipulate, you want to work off of relatively low voltage. A relatively low voltage. You don't want it working off of 100,000 volts, right? You want it to work off of relatively low voltage. So, you know, the circuit is going to be divided. If you look at the back of the chapter, I'm going to split with Bushong in his description of the circuit a little bit. Okay, usually I try to stick with test questions that would reflect what Bushong, you know, says. But I think for simplicity's sake, instead of, you see where he's showing the high voltage section? High voltage section incorporates both of these, right? Mm-hmm. I'm going to split the circuit right there instead of right there, okay? Low voltage, high voltage. All right, notice also that as he comes down, a part of the filament circuit is in the high voltage section, right? If you look at the, the filament circuit comes off down here, right? Filament circuit comes off down there, it goes through the MA selector, and it goes into the step down transformer. So we've got a lot and a little, and then that in turn comes off and it goes into the X-ray tube, right? So I'm going to call this a separate circuit. Okay, this is going to be the filament circuit, just for simplicity's sake. So low voltage, high voltage filament circuit, you can just go ahead and put that in the book. There's going to be labeling on this test, and it's not going to be that particular diagram, but if you know all the components, that diagram is going to work just fine for studying. Okay, just know that on my test, low voltage, high voltage filament circuit, just so there's no confusion about, well, where's step down transformer? Well, it's in the filament circuit. According to that, it's in the high voltage circuit. But what does a filament transformer do? Decreases voltage to like 25 volts. So how could it be in the high voltage? It just, you're going to get home and you're going to be thinking about that stuff. I'm going to simplify it. Low voltage, high voltage filament circuit. Okay? All right. So, our auto transformer, kVp selector, but we also need to know that the kVp that we set is what we're going to feed into this thing over here. Let's say our turns ratio is 1 to 1,000. Okay, let's say we feed this thing 220 volts. And we'll make it 200 volts. All right, and let's say I have half as many turns on the secondary side than what I have on the primary side. Okay? Have half as many turns on the secondary side as I had on the primary side. What's my voltage on the secondary side going to be?
100.
It's going to be 100, right. So now I've got 100 volts that I'm going to feed into the high voltage transformer, okay? So whatever actual voltage that I have here, I know exactly how much I'm going to have over here because my turns ratio is 1 to 1,000, right? So if I have over here 99 volts, because my auto transformer is off, then what's my voltage, my kilovoltage going to be?
99.
99 kilovolts, right? So what if I set, what if I set 100 and what I get is 89? Might that be a problem? Mm-hmm. Yeah, the 99 is not so much, but the 89 is getting a little squirrely, right? So we don't want that. We got to monitor how much voltage we're actually feeding this thing. So we're going to have a kVp meter somewhere over here. I don't want to confuse this, so I'm going to stick it right here. So you've got a kVp meter right there. What's the intellectual problem with that? It's just a hump to get over. It's not really a problem.
You don't have kVp.
You don't have kVp, right? So why are we going to call it a kVp meter?
Because you're protecting how much you're gonna have from.
Exactly, because this turns ratio is set. We know exactly how much we're going to have over here if this is right, and we're going to determine that that's right by looking at that. Does that make sense? So even though it's not reading kVp, it's reading what we're going to have. It's anticipation of it becoming kVp. Now, why do we have it over here? What circuit is this? Low voltage. What do you not want to deal with?
High voltage.
High voltage. So everything that you want to touch is going to be over here for the most part. There's one thing that we're going to have over here, a gauge over here, and we'll get to that maybe Tuesday. Aha! Yeah, still trying to get you in here on Tuesday. Yeah, I'm going a little long here. I didn't realize I was cutting everything off. So I can either line that up for the screens or I can line it up for the board, but I can't do both. All right, so low voltage circuit, low voltage circuit, filament circuit, high voltage circuit. Everything that we can put over here on low voltage circuit, we want to put over here on low voltage circuit. okay? kVp meter being one of them. We're going to call that, though, not just kVp meter, but what do you call something that comes before something else? Pre, yeah. So pre-K comes before kindergarten, right? So pre-K, right? This is pre-kVp, pre-reading kVp meter. It's reading the kVp, it's reading the voltage in anticipation of it becoming kVp, but it's not really kVp yet. It's a pre-reading kVp meter. Okay? So what are the characteristics of an auto transformer? You know, what all do we call it? We call it a rheostat, kVp selector, has a single winding, that just means one coil of wire, has a single winding, it's a variable resistor, variable turns ratio transformer. So when we set our kVp, we're setting the contacts on the secondary side. All right, we spread them out, kVp goes up, bring them together, kVp goes down. Right? Any questions on all that? We're good?
So as far as like location of the kVp meter, would you just say that's on the low voltage side?
Yeah, one of two things. It's either going to be in the low voltage circuit, or it will be, well, one of three things. Or it will be,
It's like hard to find where you
our
are.
ghost just gave herself a facelift. It's either going to be in a low voltage circuit, or it's going to be on the primary side of the
High voltage.
high voltage step-up transformer, or the secondary side of the auto transformer. Right. So one of those three is where it's going to be. Okay. So we've got voltage, we got kilovoltage at this point, right? Or the capability of creating kilovoltage. What we've got to do now is create MA. That's probably where we're going to end. I don't think we're going to get into timers. So we gotta have MA. All right. So we've got, again, another rheostat down here. That's your MA meter, or MA selector rather. And what this is going to do is it's going to give us the amperage that we need to heat up the filament. Okay, remembering that we don't have mass until we make an exposure. We add in the time, we create the exposure, then we have mass. But at this point, we're just creating thermionic emissions, that electron cloud, right? So whatever we select controls how hot we make that and how many electrons we have available, right? So if, let's say, our minimum is 100 and our maximum is 500, then, you know, you do the math, 5 times as hot, 5 times as many electrons, right? So that, you know, once we make an exposure, we're going to have 5 times as many electrons travel across the tube. Now we can adjust that, you know, I mean, if you're selecting a technique and the only thing that you move is your MA, it's going to be big moves, right? From 100 to 200, 300 to 500, it's going to be big moves. But you can change your MA and change your time to arrive at the same mass at exposure. Okay? So we can manipulate that. So what are the characteristics that we want in an exposure? What are the ways we control motion? We have 2 types of motion. Voluntary and involuntary, right? Exposure time being one of them. Careful instructions for voluntary motion. For involuntary motion, shortest exposure time as possible, right? So let's say we need 50 mass. How do we get to 50 mass? Could we use 500 at 1/10 of a second? Yeah, right? What if we used 100? In a word, what would I need? More. Yeah, I need more time, right? So is there a time to use that long exposure time? I haven't really gotten into any of those procedure types, but yes, there actually is. There's what we refer to as autotomo, and I'll explain what that means later on. But sometimes we need motion to blur out other things, okay? Like, and we're going to get into this, end of the semester and next semester, one or two. like whenever we're doing T-spines. When we do AP of the T-spine, you know, everything's good. Got the mediastinum, and it's all fluid filled, right? So it's looking kind of like the L-spine. But whenever we do lateral, our T-spine is going to be superimposed not just by ribs, but two lungs. You've seen a lung, right? What do they look like? They're dark, and they got squiggly lines all through, right? So if you've got a subtle fracture of a T-spine vertebra, you just can't see it all that well. But if you allow the patient to move throughout the exposure, or not move, keep them as still as possible, but breathe throughout the exposure, what's happening with those ribs and those lung markings?
They're moving.
They're moving. And what happens when things move while you're taking a picture of them? They get fuzzy, they get blurry, and if the vertebra remains still, you can actually see the vertebra better if the patient's moving. So is there a time to use low MA and long exposure time? Yes. Yeah, breathing techniques. We're going to see the sternum, spine. There's a C-spine view that we can do as well. It's called the Ottinello method. If you just wake up in the middle of the night and want to get bored with something. So Ottinello method is a movement of the jaw so that you can see the upper C-spine. So, and we'll talk about that later in the semester in positioning. So that's your MA selector. We send, through a separate circuit, electricity through the MA selector, and then we select our specific MA, and it's got to compensate for this thing, because as we send our electricity through this, what's going to happen to our kVp if we have more turns on the primary side than the secondary side? It drops, right. So your kVp is going to drop to like 25. What would that, or I'm sorry, it's not kVp, that's voltage. What would be the significance? Why would we want such low voltage? What is voltage control in the X-ray tube?
So the electrons don't get shot into the...
Bingo. We don't want the electrons to shoot across the tube before we're ready for them to shoot across the tube, right? And the distance between here and the anode, I know I draw it like that, and it's nowhere near that. It's like that, really pretty close. And we don't want that to happen, so we need low voltage. If we sent 220 volts through that, we'd have issues. Okay, so we got to drop it. It's going to drop to like 25 volts. Now when we push the prep button, we're going to have voltage low enough that electrons won't fly across the X-ray tube, but we have amperage high enough, and amperage really is going to be relatively high compared to what you're thinking. Our tube current, once we make an exposure, what do we measure our tube current in? Milliamps, right? Thousandths of amps. So our filament current is going to be quite high compared to that. It's going to be, what does he say, 3 to 5 amps? So that would be 3,000 to 5,000 milliamps, right? But what is our purpose at this point? Is it to make X-rays? Just to heat that up, right? To the point where they're boiling off, so we create an electron cloud, thermionic emissions, space charge. All mean the same thing. Okay? So we'll push our button, we'll push provided you don't go all the way through the prep button, but let's say you've got the two different buttons, one's prep, one's exposure. You push the prep button, what all happens? You get the rotor, right? So you remember the induction motor I showed you last week. So it starts firing off to make that rotor spin around and around and around, right? So you get that, and then you energize. Really the only part of the circuit that you are fully energizing at that point is this lower circuit, so that you start to flow electrons through the filament to get to the point of thermionic emissions. Now you're ready to make an exposure. Machine won't allow you to make an exposure until the rotor gets up to full speed, which usually takes about a second, and full speed is about 3,000 RPM. So if you're driving home today, take a look. I think all cars have a tachometer on them now, which is kind of silly. You might have needed a tach when you were driving a shift, stick shift, but, car's gonna shift when it's gonna shift now. But you got a tach, right? So as you're driving down the road, it's reading out in revolutions per minute. And take a look at it. You know, you're driving down a road in overdrive, 70 miles an hour. Your tach is saying that the engine is only gonna be going like 1,500 RPM. So that's going a lot faster, right? So we push the prep button, that spins, we make an electron cloud with thermionic emissions, and we're at the point of exposure. Now this is a teaser. The most complicated thing that we're going to talk about in this section is this, okay? So what do we have to make this transformer work? We have to have electric current, but that only tells half of it. Alternating electric current. We have to have alternating electric current so that we set up a changing magnetic field so that if we tap into the secondary side of the auto transformer, we're going to increase or decrease our voltage, right? So what does alternating current do? It goes in that direction, right? In that direction, and then it's going to go in that direction, followed by that direction. Do you see a potential problem? We have to have alternating current here so that we can make a changing magnetic field so that if we tap into the secondary side, we can increase or decrease our voltage. And then we're going to send that electricity here, and it's still alternating current, right? And alternating current as self-induction. We send the electricity here, it's still alternating current, so we set up a changing magnetic field, and if we move a secondary coil close enough to it, then we induce a alternating current in the secondary side of the high voltage transformer. At the same time, we send alternating current into this, right? Create a changing magnetic field. Our turns ratio is going to be less on the secondary side of the filament transformer than on the primary side, so our voltage decreases. But we set up that alternating, we send it alternating current so that it creates a changing magnetic field. So we set up alternating current in this secondary side as well. Okay, so we have to have it, love alternating current, have to have it, love alternating current, have to have it, love alternating current, got to get rid of it, hate alternating current. Okay, so we've talked about everything in the circuit, the different components of the circuit with the exception of one. Okay, we talked about conductors, superconductors. We talked about well, I just gave that away. Insulators, but what have we not expanded on? Semiconductor. So what we're going to have to do in order to get rid of the alternating current, because, you know, if we send electrons across the tube and they're hot, they can damage the rotor. Well, how thick is the rotor? It's a chunk of metal, right? So if it can damage that, what's it going to do to a light bulb filament? Destroy, right? The likelihood of sending electrons back across the tube that way, not very good. So it's probably overstated a little bit. But at the very minimum, if we don't send electrons back across the tube, then we're only using half of the wave. And so X-ray creation efficient? No. If we're only using half of the wave, how much less efficient is it? Half as efficient as inefficient. So we're going to talk about how that actually works. We're going to change our voltage waveform from alternating current to pulsating direct current with what we refer to as rectifiers. And it's just semiconductors. That's lecture for not Tuesday, but Wednesday. Yeah. All right. Any questions?